base, I'm a mobster. You got 50 whole bed, you'll be my sponsor. Them snakes on the plane, me and Kanye Conda. Yeah.
Hello and welcome to the concepts video on rates of change and behavior of graphs. So basically, let's start off from the beginning again. Let's just review a little bit. So functions can describe the relationship between your input and your output, right? Your independent variable and your dependent variable. So it's only natural that we can study the rate at which values of the function, aka the output, are changing with relation to changes in the input. So let me write that down a little bit. So we can study the rate at which values of the function, okay, values of the function meaning the output, aka output, are changing or change with relation, with, I'll just put changes in input, okay, changes in input. Okay, so namely what we want to study is actually called the average rate of change, okay? So average rate of change, that's the formal term. That's what's most important to us right now. What seems pretty useful, right? So it's useful to study, and we abbreviate this oftentimes with AROC, average rate of change, right? Instead of writing this whole entire thing out, we just put AROC, which means average rate of change. So what are some examples, some real world examples? Well, one could be like miles driven per hour, right? So like, let's say you're taking a trip, miles driven per hour. Okay, let's say you're taking a trip from, I don't know, from like Los Angeles to Las Vegas or something, and then you go X many miles in X many hours, and then you want to find the average rate at which you were driving. So then you would find miles driven per hour, right? And that's your average rate of change. It doesn't mean in each hour you drove that many miles specifically or exactly, but it means your average, what was your average speed, basically, okay? What's another example? That would be maybe like increase in, let's say, bunny, like little bunnies, bunny population, let's say per month, okay? So that's another example of an average rate of change, right? Per month, how many, about how much or how great was the increase in the bunny population. And let's do one more example here. How about a decrease in, let's say, how about a college savings account, and we'll say per quarter, okay? So that also, sadly, is a rate of change that we can study, right? And that definitely applies to real life in some way. So here's an example, and we're going to figure out how to figure out this average rate of change, okay? So it says on a road trip, so kind of like what I was talking about before with the first example, after picking up your friend who lives 10 miles away, you decide to record your distance from home over time. Find your average speed over the first 6 hours. So this first point means you haven't, well, you're picking up your friend right now who lives 10 miles away from you. And because we're measuring distance in distance from your house, that's why it's 10 originally. Anyways, so what we want to find is the average speed over the first 6 hours, okay? So here's 0 hours, okay? And then here's the first hour, second hour, okay? Third hour, fourth, fifth, and sixth. This is where we want to stop, is the sixth one, okay? So 5 and 6. We don't want to look at the seventh one at all, okay? So in order to find this average speed, so what is, just in a physical sense, so average speed in like miles per hour, right? The units actually tell you what to do, right? So miles per hour. That's what we want, miles per hour, which implies that we need some kind of distance, right? Some kind of distance quantity over time. And in this sense, we want total distance or distance traveled in 6 hours, because that's what they told us to do over the first 6 hours, right? So traveled in 6 hours. And then over time, that would be the total time. Over the total time, so this would be in fact 6 hours. So 6 hours, okay? So let's do that. So we have our initial point is 0, t equals 0, and our d of 0 is equal to 10, okay? And then we had when t is equal to 6, which means 6 hours had passed, then our d was now, d of 6 is equal to 292. Okay, so that means we traveled by the 6th hour, by the start of the 6th hour, we had traveled 292 miles from our house. That's where we were. Or our distance was that, anyways. Okay? So, in order to get this average speed, so the speed, average speed, I can't spell. Okay, average, there we go. Average and speed is equal to, so the distance traveled. So that means we traveled 292 minus wherever we started at, which is 10 in this case, divided by, so this is the distance traveled, and the total time is going to be 6 minus 0, which gives us 6, right? So this is equal to 282 divided by 6, which is equal to, that would be 47, that would give us, and this is miles per hour. Okay, so this is our average speed here. Okay, so from this example, we can kind of derive meaning like create, an average rate of change formula, right? And I'll introduce that on the next slide. So actually, our average rate of change formula is given by, so average rate of change on the interval, this is the important part, A, B. You can't just take the average rate of change in general if we don't know where we're starting and where we're ending, right? So average rate of change on some interval is equal to the change in output over the change in input over that time. In input, okay, over that interval. And oftentimes change is off, like the word or the phrasing change in is denoted by a little triangle thing, and that's a Greek letter called delta. Okay, so delta output, so that means change in. Okay, and if I can spell here, output, there we go. And then change in delta input. Okay, so what this implies is that if we were to have some function, okay, so here's our x and here's our y per se, okay, or like our f of x, ooh, moving the screen here, f of x, okay, and we were to have like a f of a, because that's the value of the function when you plug in a, right? Then we have a bunch of other values in between, then we have a b and an f of b, that makes a pair, right? And then we could have more after and even more before. But this is the interval we want to look at, right? We want to restrict it to this interval here. So this is the start point of our interval, and this is the end point, okay? So that means explicitly we can write our AROC, our average rate of change formula, as the change in output, okay? So this bottom row represents output, remember? Okay, and then this top row, the x, represents our input. So the total change in output over our interval is going to be the end point output minus the beginning point output, so f of b minus f of a, over the change in input, so that would be our ending input subtracted, or minus the starting input, so b minus a in this sense, okay? So this is going to be like the all-around formula that I would highly recommend that you know, or at least understand, for our average rate of change, okay? So let's do an example of this. Okay, so we're going to compute the average rate of change of this function, f of x is equal to x squared minus 1 over x, on the interval 2 to 4. Okay, inclusive that is. So our a is like 2, that's our starting input value, and b, which is our ending input value, would be 4 here. Okay, so let's write down our AROC formula. Average rate of change is equal to f of b minus f of a over b minus a. So in this case, our b and a, let's plug those in. So f of 4 minus f of 2 over 4 minus 2, right? So now what we need to know, okay, so the bottom is going to be 2, obviously. 4 minus 2 is equal to 2. And then, but the top, we don't really know what those are, right? F of 4 and f of 2, what are those? So all you have to do is just plug them in to our function, which was explicitly defined. So f of 2, for example, is going to be 2 squared minus 1 over 2. So this is 4 minus 1 half, which is equal to, if we get our common denominator, 8 over 2 minus 1 over 2. So that would give us 7 over 2. So that's f of 2. And then we'll do the same thing when we plug in 4. So then we'll have 4 squared minus 1 over 4. this is equal to 16 minus 1 over 4. So that's like saying 64 over 4 minus 1 over 4. So that's going to end up being 63 over 4. So these are pretty messy numbers, but, you know, we're getting the point across of how to do the process. Okay, so let's plug these in now. So our f of 4 is equal to 63 over 4. So let's plug that in. 63 over 4 minus f of 2, which is now 7 over 2, over a 2, which was the 4 minus 2 on the bottom. Okay, so let's just simplify this. Let's continue this on the next slide. Okay, so we have 63 over 4 minus 7 over 2, all over 2. And if we get a common denominator on the top there, we're going to get 63 minus 14 over 4 over 2. Okay, and then this is going to be equal to 63 minus 14 is going to be a 49, and then over 8, and when we combine the denominators, that is, and that'll be it. That is our average rate of change for the function over the interval 2, 4. Okay, so now we're going to go over something which is very much related to average rate of change, and that would be the graphical behavior of functions. Okay, so we're going to start off with some pretty basic concepts, okay? It's good to start from the basics and then build upon those. So, we're going to say that a function, f of x, or we can just say a function in general. So, a function, f of x, for example, f of x is ... and we have two options. It's either a, increasing, okay? Well, actually 3 options, but anyways, increasing on an interval, if f of x increases as x is increasing, as x increases. I'll just abbreviate with INC for increases, not incorporated, but increases, okay? So aka, for every, and this is going to be really formal and everything, but I'll explain. So for every a and b, such that a is less than b, then f of a is less than f of b. Okay, so what does that mean? We have a bunch of letters here. So this just means that, let's say we have, okay, here's a graph. Here's our x and y, right? And let's say a is here and b is here. Okay, so a and b are independent variables. Anyway, so those are just like endpoints kind of thing. So for every a and b inside here, so all of the x values, such that the x value to the left is less than the one on the right. So that basically just, yeah. Okay, so like 1 is less than 2, okay. So for every, when we're moving from left to right, let me rephrase it. So when we move from left to right, our function values better be going higher and higher. Okay, so basically something like this, or something like that. Okay, so you can see how each consecutive move, or like every time we inch a little bit to the right, a little bit to the right, a little bit to the right, our function value keeps going up and up and up. It doesn't have to go change drastically or anything. It just, each successive value of the function as we move to the right has to be greater than the value of the function compared to the left. Okay, so as we move to the right, our function better be going up, and that means it's increasing. Okay, conversely, it would be a function f of x is decreasing on an interval, if our f of x is, like I said, conversely, decreases as x increases. So for every a, b, and b, that is, such that a is less than b, then our f of a is actually greater than f of b. So that just means, again, I'll draw a graph here, okay, so x and y, here's like a and b, and now we're still moving to the right, okay, but now our function values, meaning like the height, are decreasing, okay, they're going down. All right, it's pretty, I mean, like if you see a graph, you'll be able to tell where it's increasing and decreasing because it's either going up like this or going down like that. Okay, so that's what increasing and decreasing are. And something really important, which I'll show you on the next slide.
Please. Yeah. Overseas, nigga. Top floor, clear windows, nigga. Glass house.